Standard Instrument Approach Procedures, or IAPs, allow you to safely descend by instrument reference from the en route structure to a point near the runway where a landing may be made visually. All instrument approach procedures in the United States are based on U.S. terminal procedures, commonly referred to as TERPs. TERPs outlines the criteria used to develop instrument approach procedures. Approach charts are the visual form of an instrument procedure and give you the vertical and horizontal information necessary to make a successful approach to an airport. In this segment, we'll look at what information is contained on an approach chart and how it is presented. Then we'll look at some new technology that is appearing on your approach charts. We'll begin with a look at Jeppesen approach and airport charts. Then we will turn our attention to government-issued approach and airport charts, which are produced by the National Aeronautical Charting Office, or NACO. Before beginning, it should be noted that Jeppesen does not create the criteria or devise the procedures for an approach. This is done by the governing authority in each country. In the United States, this authority is the Federal Aviation Administration, or FAA. You should also know that charts are frequently updated, ensuring you have the most current and up-to-date information. Some years ago, Jeppesen introduced a new chart format. It was tested and evaluated by human factors professionals, airline crews, and general aviation pilots. The new chart format is known as the Jeppesen briefing strip format. While not every chart in the Jeppesen approach chart library has been converted to the briefing strip format, the vast majority of charts have been redone. This program concentrates on the briefing strip format. However, it also contains a brief review of the classic Jeppesen chart style. The briefing strip approach chart format is divided into 4 sections: heading, plan view, profile view, and landing minimums. The information is arranged in a specific pattern based on how pilots review and use the chart data. Let's take a closer look at the heading portion of the chart. The information on the chart flows from right to left. On the top right side, you will find the location of the airport by city and state. All Jeppesen civil approach charts are filed alphabetically by city name within the state. The city name is shown in bold print for easy recognition. The specific procedure is noted below the city name. The name of the procedure identifies the type of approach and the primary navigation aid upon which the approach is based. It does not indicate the equipment required to fly the entire approach. It merely indicates the equipment needed to fly the final approach segment. If NDB is listed as a part of the procedure, such as it is here, NDB equipment in operating condition is required to be installed in your aircraft in order to fly the final approach segment. In the case of a VOR DME approach, you would need VOR and DME equipment. However, if the approach is titled VOR DME or GPS, either VOR DME or GPS equipment can be used to fly the approach. Both are not required. If the approach course is not aligned within 30 degrees of the runway, the approach is identified with a letter. Notice that this approach is called the VOR DME or GPS A approach. A circle to land maneuver is required to align the aircraft with the runway. The series of numbers in the center of the chart is the index number. It helps you file the chart and identify certain features. The first digit identifies the airport within a city based on an arbitrary number assigned to each airport. The second digit represents the type of approach chart and is based on the navigational aid used to conduct the approach. In this example, the number 1 represents an ILS, MLS, LOC, or SDF approach. Typically, approaches with the lowest landing minimums and greatest precision have a lower index number than approaches with higher minimums. The chart legend lists the assigned numbers for each type of chart. The third digit represents the filing order of charts that are of the same navigational type. The number 1 shown here indicates this is the first ILS approach chart for DFW. The next ILS approach chart for the same airport would be listed as number 2. The revision and effective dates are also found in the center of the chart heading. Never use a chart before the effective date. If there is no effective date, the chart is for use upon receipt. On the far left side of the chart is the 4-letter ICAO identifier for the specific airport. In this case, KDFW is the ICAO identifier for Dallas-Fort Worth International Airport. The next few rows of the heading section contain information about the approach. This includes communications, pre-approach briefing information, and MSA information. From left to right, the communications section provides the frequencies in order of arrival, such as ATIS arrival, approach, tower, and ground control frequencies. Multiple frequencies may be given for a particular facility, such as the tower frequency here at DFW. In this case, the frequency depends upon whether your arrival is from the east or the west. Also be aware of any notes or symbols in the communications row. For example, the Redbird Tower and ground frequencies do not operate continuously, as noted by the asterisk. In addition, when the tower is not in operation, you are advised to use the Common Traffic Advisory Frequency, or CTAF. In this case, the CTAF frequency is the same as the tower frequency. In select locations where a Flight Service Station, or FSS, is located on the field and can provide local airport advisories, this information is noted on the chart as it is here in Jackson, Tennessee. The second row of boxed information is designed to provide you with a quick reference of the pertinent approach-related information. From left to right, you see the primary nav aid and its frequency and identifier. At DFW, the localizer is the primary nav aid. Its identifier is ILWN, and the frequency is 109.5. Next is the final approach course. In this case, the final approach course for the ILS runway 13 right at DFW is 133. Next is the key altitude information. For a precision approach, this is the glide slope outer marker altitude. For example, the glide slope altitude at Good, the outer marker, is 2,235 feet MSL. For a non-precision approach, it is the minimum altitude at the final approach fix. Following the glide slope information is the lowest decision altitude, DA, or minimum descent altitude, MDA, depending on the approach type. The ILS decision altitude is 791 feet. Also included in the pre-approach briefing information is the airport elevation and the touchdown zone elevation. Below this row of information is a textual description of the missed approach procedure. On this particular approach, the procedure requires a climb to 1,000 feet, then a climbing right turn to 5,000 feet outbound via the TTT or Maverick VOR on the 275-degree radial to the slot intersection. Slot intersection is 35.6 DME from Maverick. Any notes that are applicable to the approach, such as altimeter setting or equipment requirements, are included below the missed approach information. In this case, radar is required for this approach. The minimum safe altitude, or MSA, is located to the right of the pre-approach briefing information. The altitude shown in each sector provides a minimum of 1,000 feet of obstacle clearance within a 25 nautical mile radius of the navigation facility. The name of the facility is listed below the circle. MSA altitudes are intended only as emergency information. Normally, the MSA is based on the primary nav aid on which the IAP is based. For RNAV and GPS approaches, however, the MSA is based on the runway waypoint, airport waypoint, or the missed approach waypoint. It is important to note, however, that if the primary navigation facility for the approach does not provide full azimuth reference information, such as an ILS, the minimum safe altitude is based on the primary omnidirectional facility in the area. The MSA circle may be broken into individual sectors of no less than 90 degrees each. Notice that the sectors are formed by magnetic bearings to the station. In this example, the north sector is formed between the 090 and 270 degree bearings to the Maverick VOR. The second major section of the approach chart is the plan view. This view provides you with the overhead perspective of the approach procedure and the surrounding airport vicinity. To help you measure distance, a mileage scale is located along the left side of the chart plan view. Typically, 1 inch is equal to 5 miles, but it may differ if the chart covers a large geographical area. Latitude and longitude lines are shown in 10-minute increments along the inside edges of the plan view. The primary airport is depicted with its corresponding runway layout. For reference, airports in the vicinity that have an instrument approach or VFR airports that underlie the final approach are shown with light shading. A star symbol indicates the airport has a lighted beacon. Several types of orientation details are also shown on the plan view of approach charts. These include ground features like major lakes or rivers, as well as terrain high points and man-made structures. Typically, only those points and structures higher than 400 feet above the airport elevation are depicted on the plan view. Remember, not all man-made structures or terrain high points are depicted on the approach chart. Various symbols are used to represent terrain high points and man-made structures. These symbols are defined in the chart legend. A bold arrow is used to point out the highest known terrain or structure. The mean sea level elevation is given next to the symbol. It's important to know that there may be other higher uncharted terrain or man-made structures. The terrain and obstruction altitudes depicted on the chart should not be relied on for descent below the minimum IFR altitudes. Terrain contour information is depicted when terrain within the approach chart plan view exceeds 4,000 feet above the airport elevation, or when terrain within 6 nautical miles of the airport reference point rises to at least 2,000 feet above the airport elevation. This information is for reference only and must not be relied on for terrain clearance. Minimum IFR altitudes published on the procedure provide terrain clearance. Nav aid symbols shown on the plan view are similar to those found on other Jeppesen charts. For example, a VOR is indicated by a compass rose. A TACAN or DME is symbolized by a serrated circle, and a VORTAC or VOR DME is represented by combining the two symbols. Localizer, ILS, LDA, SDF, and MLS course approaches are shown as a half-feathered arrow. The primary navigational aid information is shown in bold type enclosed in a shadowed box. The information boxes for other facilities depicted in the plan view are not shadowed. Each information box contains the facility name, frequency, letter identifier, and Morse code identifier. If a D appears in the box, it indicates the facility transmits DME information. The letter H in parentheses indicates this is a high-altitude VOR station. If the letter T appears, the station is a terminal class facility. And L indicates a low-altitude class VOR. If the facility is a localizer, ILS, LDA, SDF, or MLS, the nav aid information is enclosed in an oval-shaped box. On localizer back course approaches, the front course information is also included in the box. This is provided for pilots flying aircraft equipped with an HSI. Various approach transitions are also depicted on the chart to assist you during the transition from the en route structure to the initial approach fix, or IAF, especially when the IAF is not part of the en route structure. Approach transitions are flyable routes that provide a minimum of 1,000 feet of obstacle clearance. This obstacle clearance extends 4 nautical miles on either side of the charted course. You can determine if a line on a chart indicates a flyable route or is simply a radial or bearing forming a fix by noting several items. The magnetic course is shown with the course line, and the nautical mile distance is printed next to the line. The route also has a minimum altitude, such as 4,000 feet. In addition, a flyable route uses a wider, darker line than the one used to indicate a radial or bearing forming a fix. Notice the difference between the two lines that point to Pipes intersection and the line between Pipes and Argan. The lines locating Pipes intersection are simply radials from a VOR that help locate the beginning of the DME arc and the initial approach fix. They are not flyable routes. On some routes, you must fly a heading rather than receive course guidance from a navigation facility. For routes in which this occurs, the letters HDG are printed near the route. Initial approach fixes are indicated on the plan view with the notation IAF. In this example, there are 3 initial approach fixes, one at Caps, one at Pipes, and one at R059, which is the 059-degree radial 14 DME from the Gregg County VOR. An initial approach segment is shown extending from each of these IAFs. If a course reversal is authorized, it is depicted on the plan view. When this type of symbol is used, you may reverse course any way you desire as long as you stay on the same side of the radial as depicted on the chart, which allows you to remain within the protected airspace. You must also stay at or above the minimum altitudes and within the distances shown on the profile view. When a procedural track is charted, as shown here, or depicted as a holding pattern like this, you must fly the procedure exactly as shown unless you are being radar vectored to the approach course. When the notation "No PT" appears, a procedure turn is not required or authorized. The next segment of an approach is the intermediate segment. It may begin at an intermediate fix, IF, or when you are aligned with the final approach course after flying the DME arc or the procedure turn, and ends at the final approach fix. While flying the intermediate segment, you have a minimum of 500 feet of obstacle clearance. The width of this segment tapers from 4 nautical miles on either side of the course at the start of the segment, down to as little as 2 nautical miles at the final approach fix. The final approach segment begins at the final approach fix. On a precision approach, this is the point where you intercept the glide slope at the minimum glide slope intercept altitude. This interception usually occurs near the outer marker, which in this case is good. The final approach segment ends at the runway or at the missed approach point, whichever is encountered last. The missed approach course is indicated by a dashed line on the plan view. When information concerning the missed approach continues off the plan view, an inset is provided. The inset area is not drawn to scale. Now let's discuss the profile view of Jeppesen approach charts. The profile section of the chart is a side view of the procedure, but unlike the plan view, is not drawn to scale. This view depicts the altitudes, fixes, distances, and magnetic courses to be flown. The dominant feature of the profile section is the heavy solid line representing the flight path. Before glide slope interception, this line represents the flight path for both the precision ILS and non-precision localizer approach. Beyond the glide slope interception point, the solid line represents the ILS approach. The localizer approach path is depicted by a dashed line. On a non-precision approach, such as this VOR approach at Dallas-Fort Worth, the flight path is represented by a heavy solid line from the beginning of the approach to the missed approach point. Several altitude types also may be portrayed in conjunction with the flight path line. Unless otherwise noted, profile views depict minimum altitudes. However, an altitude may be listed as mandatory, which means you must cross the specified fix at the given altitude. Altitudes may also be depicted as maximum altitudes. If the approach requires a course reversal, it is depicted in the profile view along with the altitudes and outbound and inbound course. Additional information about the course reversal is noted in the plan view. The number enclosed in parentheses below or beside the MSL figure indicates the height of the flight path above the runway touchdown zone, not the height above the ground. In this example, you are 1,646 feet above the runway touchdown zone. There may be a notation shown in the profile view such as 10 nautical miles. Notes such as these indicate that a procedure turn is required for the approach, and they give procedure turn limits in distance or time. In this case, you must complete the procedure turn within 10 nautical miles of the fix from which the outbound track began. On this approach, the two facing arrows indicate you must use a holding pattern as your course reversal. You can find the direction of turns on the plan view. 1-minute legs are specified for this holding pattern, and both legs are flown at 2,400 feet. The final approach fix, or FAF, marks the beginning of the final approach segment on an ILS approach. The FAF is located at the glide slope intercept point when at the minimum altitude. For this approach, the final approach fix is just prior to reaching Good, where the solid line begins a descent. The notation GS 2,235 represents your altitude as you pass Good when on the glide slope. For the localizer, glide slope out, or non-precision approach, the FAF is identified by the cross symbol. For example, you cannot begin your descent from 2,300 feet until you reach the non-precision final approach fix at Good. For a localizer-only approach, the dashed flight path indicates a descent from Good to the missed approach point, or MAP, as identified by the letter M. Notice that this non-precision localizer-only approach includes various step-down fixes, such as a DME distance fix like D3.4, which are used to help you descend to a lower altitude and avoid obstacles along the approach path. The flight track continues to the point at which it turns sharply upward, ending with an arrowhead. This shows the beginning of the missed approach procedure. The missed approach point for a precision approach is based on reaching the decision altitude, DA. It is typically shown close to the middle marker where the solid line indicates climbing flight. When you reach the DA, you must make an immediate decision to continue or to execute a missed approach. The threshold crossing height, or TCH, is listed to show the height above the runway threshold where your aircraft's glide slope antenna will be if you maintain the ILS glide path to touchdown. A threshold crossing height is not shown on non-precision approaches. The touchdown zone elevation, or TDZE, is shown next to the runway symbol. This is the highest elevation in the first 3,000 feet of the landing surface. It may be different than the airport elevation, which is the highest point of an airport's usable runways. Two sets of numbers indicating distances expressed in nautical miles may be located near the bottom of the profile view. The numbers below the line relate to the distance from the landing threshold. Those numbers above the line represent nautical mileage between fixes. In this case, the distance between Ipamee and Uhizo is 5 nautical miles. Now let's take a look at a few variations that may appear in the profile view of an approach chart. It is important to look at some of these differences. However, keep in mind that additional information can be found in the chart legend pages. The circled number refers you to a note located elsewhere in the profile view. This note indicates that when authorized by air traffic control, you can fly at a lower altitude of 2,300 feet when crossing Maury and Papa. This is in lieu of the 3,000-foot altitude listed on the chart. Some non-precision approaches incorporate a visual descent point, or VDP. It is represented by the symbol V on the profile view. It is the location where you may begin a normal descent from the MDA if you have the runway threshold, approach lights, or other identifiable markings of the runway environment in sight. If VASI lights are installed at the airport, your aircraft should be on the VASI glide path at the visual descent point. This VDP is identified by the D4.7 DME fix. This point is an advisory fix, as noted by the thin vertical line. Now let's turn our attention to the conversion table located below the profile view. For a precision approach, the conversion table relates the aircraft's ground speed to the rate of descent necessary to maintain the glide slope. For example, the table shows that at ground speed of 120 knots, your descent rate needs to be approximately 647 feet per minute to stay on the glide slope. In this case, the glide slope is based on a 3-degree descent angle. Depending on the type of approach you're flying, different information may be included in the conversion chart. For non-precision approaches, the bottom line of the conversion chart usually includes the elapsed time from the final approach fix to the missed approach point. It applies only to non-precision approaches because the MAP location for the non-precision approach is usually at the runway threshold and the approach can be timed. Whereas the MAP for an approach using glide slope information occurs approximately 1/2 mile from the threshold when you reach the decision altitude while on the glide slope. When the conversion table is blank, the missed approach point is not based on elapsed time or ground speed, but rather is a specific point. The MAP in this example occurs at the NDB, which is located on the airport. To the right of the conversion table is the lighting box. The lighting box displays a symbol that represents the type of lighting installed for a straight-in landing runway. The symbols for each type of lighting are listed in the chart legend. When ALS is listed, the configuration of lighting is unknown. Also note, when PAPI or VASI are depicted in the lighting box, it is shown either on the left or right side of the runway. This corresponds with the side of the runway on which the lighting system is actually installed. When the lighting box is blank or omitted, the runway has no approach lighting. The missed approach information is found next to the lighting box. Here, icons offer a quick graphic depiction of the textual missed approach procedure. In this case, 4 icons are used. First, climb to 1,000 feet. Then make a climbing right turn to 5,000 feet outbound via the Maverick VOR on the 275-degree radial until you get to slot intersection. This should match the textual description of the procedure. The approach chart legend in the front of the airway manual explains other icons that may be used to depict the missed approach procedure. Because each missed approach is unique, read the procedure carefully and compare it to the missed approach track portrayed in the plan view to make sure you fully understand the procedure. When a missed approach procedure calls for a turn, it's important to understand that the obstruction clearance criteria are figured from the missed approach point. Do not begin a turn until you have reached the missed approach point. The last major portion of this chart is the landing minimum section, which outlines the minimum altitude you can descend to on the approach and the minimum visibility required for the approach. Landing minimums usually increase when a required component or visual aid becomes inoperative. Jeppesen charts present this information in a logical sequence. For instance, the lowest minimums for the approach are located on the left side of the box. As you move to the right, the minimums increase. On most approach charts, the minimums table represents two groups: straight-in approaches and circle-to-land approaches. On ILS approach charts, the straight-in landing section is further divided into minimums with and minimums without the glide slope. On the left side of the minimums box, aircraft categories are represented by the letters A, B, C, and D. The minimums depend upon the category of aircraft you are flying. The FAA has established 5 approach categories based on an aircraft's approach speed. For the most part, the last category, Category E, is not shown on approach charts since it applies only to military aircraft. The approach speed of a particular aircraft is computed as 1.3 times the stalling speed in the landing configuration at maximum landing weight. Most single-engine general aviation aircraft fall into Category A. The first column of an ILS approach is designated as full. The minimums within this column apply when all components are operational. In this example, no matter what category of aircraft you are flying, you can descend to a decision altitude of 791 feet MSL, which is 200 feet above the touchdown zone elevation. Notice that these figures are labeled DA parentheses H. The DA, or decision altitude, is the MSL altitude at which you must make your decision to execute a missed approach or to continue the approach. The DH, or decision height, is shown in feet AGL within the parentheses. For the full ILS, you also must have a touchdown runway visual range of 1,800 feet. Or if RVR is not reported, a visibility of 1/2 statute mile. As you move to the right, you can see how the visibility requirements change for various inoperative lights. If more than one component is inoperative, you must use the more restrictive minimum. For example, if both the runway alignment indicator light system and the approach light system are out, use the minimums listed in the rail or ALS out column. For the localizer, glide slope out, or non-precision approach, the figures are labeled MDA parentheses H. The MDA, or minimum descent altitude, is the MSL altitude below which descent may not be made without visual reference. The H, or height, above touchdown is shown within the parentheses. Sometimes sidestep landing minimums also will be published. Typically, these minimums are higher than for the straight-in runway. This allows you to fly an approach to one runway and then land on a parallel runway. On the far right of the chart are the circle-to-land minimum altitudes, heights, and visibilities. Remember, not all approaches offer circle-to-land minimums. The protected airspace during a circle-to-land maneuver depends on your aircraft's approach category. The airspace ranges from 1.3 nautical miles from the runway end for Category A aircraft to 2.3 nautical miles for Category D aircraft. Remember, if you're flying the maneuver at an indicated airspeed that's faster than the maximum limit of the speed range for your category of aircraft, you must use the higher minimums. Otherwise, you might not have the necessary obstacle clearance. The altitudes in parentheses show heights above the airport. These numbers are not based on heights above the touchdown zone because circling minimums are not referenced to a specific runway. A note on this chart indicates that circling approaches are not authorized east of runway 16 left and 34 right. While there are many reasons for a note of this type to be published, one reason may be obstructions within the circling approach area. Again, it's important to look at some variations within the minimums box. On this approach, there is a decision altitude and height penalty when using a remote altimeter setting. This example shows an approach that doesn't have straight-in landing minimums. Remember, straight-in landing minimums are omitted when the final approach is not aligned within 30 degrees of the runway, or if an excessive rate of descent, generally over 400 feet per nautical mile, would be required between the final approach fix and the missed approach point. On the other hand, you are not prohibited from landing straight in when an approach does not show straight-in landing minimums, provided that you break out in time to position the aircraft and make a normal final descent to the runway. Notice that there are different minimums for this approach depending on whether or not you can identify a specific DME fix. Since it is a step-down fix, once you have identified it and crossed it, you can descend to the lower minimum altitude. As you begin to investigate the different types of approaches, you may encounter Category 2 and 3 approaches. Category 2 and Category 3 ILS approaches use the same basic format as a standardized ILS. However, you must be a Cat 2 or Cat 3 authorized pilot and have a Cat 2 or 3 equipped aircraft to use the approaches. Typically, they have lower approach minimums than a standard ILS and may list multiple decision altitudes based on operator requirements and equipment. For example, a Cat 2 decision altitude is normally 100 feet above the touchdown zone elevation. As a pilot, it is prudent to thoroughly read and understand the profile view of the chart. If there is something noted on the chart that you haven't seen before, refer to the chart legend and the Jeppesen Chart User's Guide for further information. Finally, if any changes were made to the chart during the last revision cycle, they will be noted along the bottom edge of the chart. In this example, the MSA altitude was changed. The information we've covered so far is primarily aimed at traditional approaches, such as ILS, localizer, VOR, and NDB approaches. But the world of aviation navigation is changing rapidly, and so are approach charts. This next segment is designed to explain the changing technology and terminology that you'll see on Jeppesen approach charts. With the widespread deployment of area navigation systems and the advent of satellite-based navigation, greater flexibility in defining routes, procedures, and airspace is now possible. To capitalize on the potential of these new technologies, the FAA, in conjunction with the International Civil Aviation Organization, ICAO, has introduced a new standard of navigation and airspace management called Required Navigation Performance, or RNP. The theory behind RNP is to establish one performance standard that applies to aircraft, airspace, pilots, air traffic controllers, and international aviation authorities. This single performance standard is enabling the widespread use of area navigation, or RNAV. The term RNAV no longer refers solely to the VOR station mover of the past, but rather encompasses several different types of navigation equipment. The heading RNAV applies to GPS, INS, VOR DME, and LORAN-based navigation systems. When a specific RNP standard is given, such as the ability to maintain a course of 1 nautical mile on either side of a course line, it doesn't matter how the RNAV system calculates position, as long as it provides navigation that meets the specified required performance. A given RNP level is applicable to a specific route, airspace, or procedure. The RNP value is expressed as a distance in nautical miles. Currently, in the United States, there are 3 RNP levels: 0.3, 1.0, and 2.0, but additional RNP levels will be added. RNP 0.3 represents a distance of 0.3 nautical miles, or 3/10 of a nautical mile, on either side of a specified center line. At the present time, a 0.3 RNP level is the highest level. An example of this RNP level is the specific performance required on the final approach segment of an instrument approach. An RNP level of 1.0 is typical of that used to define a terminal route. and an RNP level of 2.0 is the width typically used for en route operations. You need to have a clear understanding of the aircraft requirements for operation in a given RNP environment, and advise ATC if an equipment failure or other malfunction would hinder your operating ability within the designated RNP airspace. When appropriate, the applicable RNP level will be depicted on IFR charts. For example, the Baltimore, Maryland RNAV GPS runway 10 approach chart includes a notation GPS or RNP 0.3 required. Aircraft that meet RNP criteria have an appropriate entry in the aircraft flight manual or its approved supplement, including any conditions or limitations. The implementation of a worldwide RNP standard marks the beginning of a fundamental change in air navigation. The FAA, in cooperation with the aviation industry, is designing an entirely new system of navigation to take advantage of these changes. The next generation of air navigation will be a satellite-based system. It will be known as the GNSS Landing System, or GLS. GNSS stands for Global Navigation Satellite System. The major component of this system is the GPS satellite system currently in use. GPS signals will be augmented by ground-based stations known as WAAS, or Wide Area Augmentation Systems, and LAS, or Local Area Augmentation Systems. GLS will allow GPS to be used for non-precision approaches as well as Category 1, 2, and 3 precision approaches. GPS and other area navigation systems are becoming more commonplace as new electronic navigation equipment is being developed and installed in commercial as well as general aviation aircraft. In order to support the full integration of area navigation into the National Airspace System, the FAA has developed a new charting format for all RNAV instrument approach procedures. This format incorporates all types of approaches that use area navigation systems, including ground-based, satellite-based, and other approach-approved systems. The goal of the new RNAV charts is to avoid the unnecessary duplication of charts. All GPS approaches, both unaugmented, today's GPS, and augmented, WAAS and LAS when operational, are published using the same new chart format. The approach is titled RNAV, parentheses, GPS, and the runway number. The Tallulah-Vicksburg GPS runway 18 is now the RNAV, parentheses, GPS runway 18. Also, when multiple RNAV approaches to the same airport runway exist, the procedure name includes a letter code beginning with the end of the alphabet. The Baltimore-Washington International Airport has the RNAV GPS Zulu runway 15 right and the RNAV GPS Yankee runway 15 right approaches. One of the approaches contains LNAV, VNAV, lateral and vertical navigation minimums, while the other approach includes LNAV, lateral navigation minimums only. Another change in the heading section is the way decision altitudes are portrayed. The lowest decision altitude or minimum descent altitude is still given. However, it is referred to as the LNAV VNAV DA parentheses H or the LNAV MDA parentheses H. New notes will also show up on RNAV charts in the heading portion of the chart. You may see requirements for the approach such as radar required, GPS or RNP 0.3 required, DME RNP 0.3 not authorized, and Baro VNAV not authorized below -15 degrees Celsius. Some RNAV systems utilize barometric pressure readings to generate a computer-guided vertical navigation path. This is called Baro VNAV, and in this case, it is not authorized for use below -15 degrees Celsius. Some systems calculate lateral positions based on DME readings. If your system operates by DME triangulation, you are unable to use the LNAV, VNAV minimums for the Yankee Runway 15 right approach. Since every system operates in a different manner, you must have a thorough understanding of the operational capabilities of your GPS or FMS system in order to comply with these requirements. The MSA on RNAV charts also contains an important difference. The MSA is predicated on a waypoint, such as the missed approach waypoint, instead of a navigational facility. However, the MSA does not exist on all RNAV charts. Rather, a terminal arrival area, or TAA, is incorporated into the approach and acts as an MSA. A TAA provides an efficient method for aircraft to transition from the en route structure to the terminal area for an RNAV approach. TAAs are charted on the plan view to represent one of three arrival areas: left base, right base, and straight-in arrivals. The TAA also provides multiple initial approach fixes as well as an intermediate fix for the approach and are designed to reduce the need for procedure turns. Flyover and flyby waypoints are also in the plan view. A flyover waypoint is depicted by a four-pointed star with a circle around it. This type of waypoint is typically used for a missed approach point or missed approach holding point when it represents a specific point in space that must be flown over. A flyby waypoint is typically a position in which a change in the course or procedure takes place. It is represented by a four-pointed star. You can anticipate and begin your turn prior to reaching the waypoint, resulting in smoother transitions. Now let's take a look at the different things you may encounter in the profile view of an RNAV chart. To further enhance aircraft operations using RNAV approaches, vertical navigation information is published in the profile view. This symbology represents vertical descent information that is coded into the navigation database. It provides guidance to allow for stabilized, constant rate descents on selected non-precision approaches. The VNAV information in the profile view illustrates the geometric descent path and descent angle from the final approach fix to the threshold crossing height at the approach end of the runway. The descent angle appears in brackets along with the descent path. Notice the descent path is a screened dotted line. The descent angle and ground speed information can also be found in the conversion table on the chart. The TCH, or the height at which the descent angle crosses the runway threshold, is also depicted in conjunction with the descent angle. The actual height in feet is stated over the end of the runway. The inclusion of VNAV descent angles does not preclude the use of minimum descent altitudes or missed approach points. You cannot descend below the MDA unless the required visual cues are present. One very important change to the profile view is the appearance of notes on some non-precision approaches. In the profile view of this VOR DME approach, you see a ball flag and a note stating, "Only authorized operators may use VNAV DAH in lieu of MDAH." This tells you that the DAH operational techniques apply to operators who have obtained permission from their controlling authority. Use of the DAH operational technique is subject to appropriate flight crew training, proper equipment, and operator approval. Contact your local FSDO for more information regarding the authorized use of VNAV decision altitudes. Also new to the profile view of selected Jeppesen RNAV approach charts is the addition of a figure that denotes the distances from the last fix to the decision altitude and the decision altitude to the missed approach point. On this chart, the distance from the last fix to the decision altitude is 0.8 nautical miles, and it is 1.1 nautical miles from the decision altitude to the missed approach point. The last major difference you will find on RNAV charts is a new descent minimum format and new terminology. The new RNAV chart format may include as many as 3 approach minima. LNAV, VNAV, LNAV, and circling. LNAV, VNAV identifies minimums developed to accommodate a non-precision RNAV instrument approach with lateral and vertical guidance. Aircraft capable of using LNAV, VNAV minimums will make their final descent using a descent path generated by onboard navigation equipment. Since vertical guidance is provided, the minimums will be published and flown as a decision altitude, even though it has higher non-precision approach minimums. When determining your ability to use the DA for LNAV, VNAV minimums, you must take into account the notes listed above the plan view on the charts that were previously discussed. LNAV minimums are designed for non-precision approaches that only provide lateral navigation. Because vertical guidance is not provided, the minimums will be published as an MDA. RNAV approaches and procedures are rapidly increasing in number. As this new technology becomes more commonplace among pilots, it is important to remember the burden rests on the pilot when determining the ability to use RNAV procedures. Information is continually added to FAR and AIM publications in order to expand the use of RNAV. Contact your local FSDO if you have any questions regarding the use of your navigation system for RNAV operations. Now that we have reviewed Jeppesen approach charts, let's take a look at airport charts found in your airway manual. When you're in the air, you have plenty of chart references to help you locate your position in reference to the ground. But once you're on the ground at an airport, orientation can become a challenge, especially at an unfamiliar airport. Therefore, Jeppesen publishes airport charts, which are valuable sources of information and can aid in the reduction of surface movement collisions. Usually, you will find the airport chart on the reverse side of the first approach chart for each airport. As you will notice, the airport chart is laid out in a manner similar to the Jeppesen approach charts. The general layout can be broken down into the following 5 major sections: heading, communications, airport plan view, additional runway information, and takeoff and alternate minimums. Some airport charts published for larger airports span 2 pages. As with the Dallas Love Field chart, the primary diagram is on the front, and additional information about runways and lighting is shown on the back. Let's take a closer look at the heading information. In the heading section, on the far right side of the chart, is the city and state in which the airport is located, the name of the airport, and the airport reference point as defined by longitude and latitude. The chart index number and chart date, or the effective chart date, are under the Jeppesen logo. On the far left, you will see the 4-letter ICAO identifier, the airport elevation, and the bearing and distance to the airport from a VOR DME or VORTAC within 40 nautical miles. The next section on the chart is the communications row. This design is similar to the one found on the approach charts in that all frequencies are shown in the order in which they are most commonly used. In this case, they are shown in the order used for departure. On the far left side of the communications row, the ATIS frequency for the airport is listed. Note that in the ATIS box, a small note says VOT 113.3. This tells you that a VOR test signal is available over the listed frequency. Following the ATIS frequency is a listing for ACARS and TWIP. This indicates that an electronic data link is available through the Aircraft Communications Addressing and Reporting System, commonly referred to as ACARS. The service provided is the Terminal Weather Information for Pilots System, or TWIP, which delivers terminal weather information to the cockpit. Following this service are listings for clearance delivery, ground control, and tower frequencies. The last box in the communication row contains the regional departure frequencies. If an R is noted after the departure frequency, radar is available. The plan view on the airport chart depicts a diagram of the airport, including the runways, taxiways, and buildings. The scale of the charts varies, so a bar scale is provided to indicate diagram dimensions. Longitude and latitude tick marks are printed along the four sides of the plan view. This helps you determine your exact location if your aircraft is equipped with a lat-long-based navigation system. The airport diagram depicts the layout of runways and taxiways. To avoid confusion, the runways are shown in black, while taxiways and ramp areas are printed in gray. The runway number, the runway elevation, and when available, the exact runway magnetic bearing are depicted on the ends of the runways. There are several symbols included in the plan view to help better orient you with the airport environment. These symbols include a bar across the runway, indicating a displaced threshold. If an approach lighting system is installed, a symbol showing the lighting array appears next to the specific runway. When appropriate, taxiways are also labeled with letter designators. Notice that taxiway Charlie parallels runway 13 right and 31 left. Positions of windsocks are marked, as well as blast fences and building locations. Also included on the plan view are roads, railroad tracks, and obstructions such as trees, buildings, and towers. The Airport Reference Point, abbreviated ARP, shows the intersection of the geographical coordinates published for the airport. Keep in mind that an ARP may not be designated for every airport. A complete description of each symbol used on the chart can be found in the approach chart legend. The additional runway information section presents more detailed information than can be shown on the plan view. Typically, this information would be shown on the lower portion of the chart. In the case of Dallas Love, however, this information is shown on a separate page because of the sheer amount of information available. This section includes a listing of each runway with its lighting systems, including VASI or related systems, and whether the runway is grooved. Also included are the usable lengths of the runways beyond the threshold and beyond the point abeam the glide slope transmitter to the end of the runway. The usable takeoff distance is also provided if the runway takeoff length is restricted. In this case, the takeoff is not restricted. Information regarding land and hold short distances and other pertinent LASO information is also printed in this section if LASO operations are conducted at the airport. Dallas-Fort Worth International Airport does conduct LASO operations as depicted on this chart. The last column shows the width of the runways. The bottom portion of this section identifies special runway information if applicable. This information is noted by ball flags in the runway column. The last section of the airport chart shows the takeoff and alternate minimums. Obstacle departure procedures are specified if applicable. The specific departure procedure for each runway is contained in a textual format. Within this section, the standard and lower than standard takeoff minimums for individual runways or groupings of runways are shown for commercial operators and air carriers. For example, the STD column under each grouping reflects the standard takeoff minimums prescribed in the FARs for aircraft with 1 or 2 engines or for aircraft with more than 2 engines. Remember, if you're operating under Part 91, you are not required to comply with the published IFR takeoff minimums. However, you should realize these minimums have been established for the operation of commercial aircraft. Therefore, it is wise to comply with the standard minimums. Also bear in mind that the publication of lower than standard minimums does not authorize use by a given commercial operator. To be able to use the lower minimums, commercial operators must obtain approval in their operation specifications. At Alliance Airport in Fort Worth, Texas, if the centerline lights and runway centerline markings are available on runway 16 left and 34 right, some operators can take off with as little as 600 RVR, providing there are at least 2 out of 3 operational transmissometers. The next column, entitled Adequate Visual Reference, is another lower than standard category that may be permitted for some operators. What this means is that you must have a visual reference that allows you to continuously identify the takeoff surface and maintain directional control throughout the takeoff run. This is usually provided by runway markings or lighting. In addition to visual requirements for takeoffs, some airports require a minimum climb capability. Notice that at Dallas Love, in order to take off on 13 left or 13 right, you must be able to maintain a minimum climb rate of at least 280 feet per nautical mile until reaching 1,600 feet. The alternate airport weather minimums are published on the chart and may be shown either on the far right side of the chart or on the bottom of the chart below the takeoff minimums. These minimums are listed only when the airport may be used as an alternate on your flight plan. When the airport is not authorized as an alternate, the notation NA appears in the box, as is the case for Spinks Airport in Fort Worth. Remember, it's important to always review the charts you intend to use for a given instrument flight. Planning and preparation before taking off will make you a safer and more competent instrument pilot. While the majority of charts in the Jeppesen chart library have been converted to the briefing strip format, there are some that are still in the classic format. Until the changeover is complete, you will need to be familiar with both types of charts. While both styles feature essentially the same information, the format in which it is presented is somewhat different. A description of the symbols is found in the approach chart legend. The classic approach chart can be divided into 5 sections: the heading, plan view, profile view, landing minimums, and the conversion table. The heading section identifies the city, state, and airport name, the instrument approach procedure, the primary approach facility, airport elevation, the minimum safe altitude information, or MSA, and communications frequencies in the order of use for arrival. The chart date, index number, and effective date, if appropriate, appear in the same location as on the briefing strip charts. The plan view portrays the overhead view of the approach. Symbols used in the plan view are the same as those used in the briefing strip format chart. One significant difference is that general procedural notes are contained within a single box in the plan view. In the profile view of the chart, the flight path, facilities, and altitudes are depicted. The threshold crossing height and touchdown zone elevation are also shown. The depiction is similar to the briefing strip format. The textual missed approach procedure is included just below the profile view of the chart. Missed approach icons are not shown on the classic Jeppesen chart format. Just below the missed approach procedure are the landing minimums. Both the classic and the briefing strip formats present the same information. The last section on the classic chart format is the conversion table. This table provides information about the descent rate and timing, depending on the type of approach. Both chart formats show the same type of information, but in the briefing strip format, the conversion chart is located above the minimum section. Now let's turn our attention to airport charts. The Jeppesen Airport chart is a valuable resource for maintaining situational awareness and orientation, as well as reducing surface movement collisions and runway incursions. Usually, you will find the airport chart located on the reverse side of the first approach chart for each airport. Like the approach chart, the airport chart is laid out in 5 sections: heading, communications, airport plan view, additional runway information, and takeoff and alternate minimums. The heading contains the name of the city and state, the airport identifier, the airport name, location information such as latitude and longitude, and bearing and distance from a VOR, DME, or VORTAC, the airport elevation, and local magnetic variation. The chart index number and chart date or effective date are located at the top center of the chart. The communications box shows frequencies in the order used for departure. For example, this chart shows the frequencies for the AWAS 3, the Unicom CTAF, and finally, the center frequency. The airport plan view depicts the layout of runways and taxiways, as well as selected surface features in the airport environment. A complete description of all symbols used on the chart can be found in the approach chart legend. The additional runway information section presents more detailed information than can be shown on the plan view. Typically, this information is located below the plan view, but in some cases, it is published as a separate page. The information on this chart includes lighting systems, usable lengths and widths of runways. Appropriate notes are also included. The last section of the airport chart shows the takeoff and alternate minimums. Within this section, the standard and lower than standard takeoff minimums for individual runways or groupings of runways are shown for commercial operators and air carriers. Remember, if you're operating under FAR Part 91, you are not required to comply with the published IFR takeoff minimums. However, you should realize that these minimums have been established for the operation of commercial aircraft. Therefore, it is wise to comply with the standard minimums. The alternate airport weather minimums are published on the chart and may be shown either on the far right side of the chart or on the bottom of the chart below the takeoff minimums. These minimums are listed only when the airport can be used as an alternate on your flight plan. The NA on this chart shows that it cannot be filed as an alternate. Although the classic charts will eventually be replaced with the briefing strip format, you will need to be comfortable using both styles during the transition period. With a little practice, you will find both chart formats clear and easy to use. The National Aeronautical Charting Office, or NACO, is the branch of the FAA responsible for publishing government-issued aeronautical charts. NACO has made several changes to their chart format and content. We will look at the NACO Pilot Briefing Information format and then briefly review the traditional NACO format. NACO approach charts are bound in booklets, each covering a specific geographic region. These booklets are entitled U.S. Terminal Procedures and contain approach charts listed alphabetically by city name. If multiple airports exist for one city, each airport is listed alphabetically under the city name. A NACO approach chart is divided into 5 different sections: the Pilot Briefing Information section, the Plan View, the Profile View, the Minimums section, and the Airport Sketch. The top right side of the NACO chart shows the approach type and runway number for that specific approach, along with the airport identifier, name of the airport, and the city the airport serves. the city and state are also printed in the top left corner of the chart. A boxed row of information begins at the top left of the chart. This is the first of 3 rows in the pilot briefing information section. Information given in this top row includes the primary procedure navigation information, the final approach course, the runway landing distance available, the touchdown zone elevation, and the airport elevation. In this case, the primary navigation aid for the approach is the localizer on a frequency of 111.9, and the final approach course is 147 degrees. The available landing distance for runway 15 left is 12,001 feet, and the touchdown zone elevation and airport elevation are both 97 feet. The second row contains procedure notes, approach lighting symbology, and a textual description of the missed approach procedure. The notes section contains special instructions or restrictions for flying the approach. Symbols are also used to indicate non-standard procedures at the airport. For example, the A in this box indicates the alternate minimums are not the standard 602 for precision approaches. Specific details for this airport are listed in the IFR alternate minimums section in the front of the chart booklet. For this airport, the alternate minimums for the ILS runway 15 left approach for categories A through D are 702. If a T appears in this section, the airport has either non-standard takeoff minimums or a published IFR departure procedure. Refer to the airport listing in the takeoff minimums and obstacle departure procedures section in the front of the chart booklet. In this case, Galveston Shoals International has both non-standard takeoff minimums and an IFR departure procedure listed. The lighting box typically depicts a lighting symbol, the lighting system type, and a circle with a letter and number inside. This particular approach has a Mulser or medium intensity approach lighting system. You can find symbols and abbreviations in the legend at the front of the book. The last box in this row contains the textual description of the missed approach procedure. This missed approach calls for a climb to 2,000 feet, then a left turn via the Humble 082 degree radial to the Cosby intersection at 21.8 DME from Humble. And finally, the third row of information contains the radio frequencies in the order in which they are normally used during the approach: ATIS, approach control, tower, ground control, and clearance delivery. Multiple frequencies for a particular facility may be included on the chart. In this case, there are multiple approach, tower, and ground control frequencies. The frequency typically depends on your geographic position in relation to the airport. A star next to a radio frequency name indicates that the facility operates only part-time. If the tower facility is in operation only part-time, the CTAF frequency also will be listed, or simply noted if it is the same radio frequency. Additional information on the facility can be found in the Airport Facility Directory. Another symbol you may see in the communications boxes is a circle with an L inside. This indicates that pilot-controlled airport lighting is available and activated through the listed frequency. Now let's turn our attention to the plan view. This portion of the chart depicts an overhead or bird's-eye view of the approach area and the procedure itself. It may include terrain, obstacles, flight paths, navigation facilities, intersections, and approach fixes. The area inside the solid circle is always charted to scale. This circle usually has a radius of 10 nautical miles. Locations outside the circle may not be to scale. A bold diagram of the runway layout indicates the primary airport. Typically, other airports in the vicinity are not depicted on NACO charts. Obstacles or spot elevations are shown with their MSL heights. The symbol for the highest obstacle or spot elevation contains a bold dot and an enlarged altitude number. This information is for reference only and must not be relied on for terrain clearance. Minimum IFR altitudes published on the procedure provide terrain clearance. Terrain contours are another feature appearing on some of the newer NACO charts. Contours will be added to charts over the next few years. Contours are added when the terrain is at least 4,000 feet above the airport elevation or is more than 2,000 feet above the airport elevation within 6 nautical miles of the airport reference point. This chart happens to meet both criteria. You'll also see a small circle on the plan view which shows the MSA or minimum safe altitude. The MSA provides 1,000 feet of clearance over all obstacles within 25 nautical miles of the nav aid. The identifier for the nav aid is at the top of the circle. In this case, the MSA is 3,100 feet and is based on the Marby LOM or Locator Outer Marker. Navigation aids are depicted on the plan view along with approach markers, such as the Locator Outer Marker or the Middle Marker. Information boxes are provided for all nav aids shown on the approach. The primary nav aid used for the approach is enclosed in a box with bold black lines. Here, the primary nav aid is the localizer. The frequency is 111.9 and its identifier is IHSQ. Feeder routes, such as this route from the Humble VOR, are flyable routes that help you transition from the en route structure to the approach. These radials and bearings are shown with heavy lines along with the altitude, course, and distance information. Some radials or bearings are not meant to be flown, but are shown to define position fixes, such as this radial that defines the snack intersection. They are depicted with a thin line with the radial or bearing information, but no altitude. When you see this line break symbol, it means that the distance to the nav aid is not drawn to scale. The initial approach fix for the approach is indicated on the plan view by the letters IAF. There may be more than one initial approach fix for the approach to accommodate arrivals from different directions. The IAF is used to align your aircraft with the approach course. Heavy bold lines identify all procedural tracks that are part of the approach procedure. At a minimum, these tracks include the magnetic course and may include altitude and distance information. The procedural tracks may include an inbound course, a procedure turn, or a DME arc. The procedure turn provides for a course reversal and interception of the final approach course. It shows the outbound and inbound headings for the turn. A barb symbol shows the direction of the procedure turn. Although you can reverse course using any maneuver, it must be performed in the direction of the barb symbol. If a holding pattern symbol is shown for the course reversal, it must be flown as charted. In this case, both an outbound and inbound course are provided, as well as the length of the legs. A DME arc also provides a means to intercept the final approach course. Since a procedure turn is not normally required, a note, "No PT," is included. The chart shows the nav aid identifier and encloses the DME distance in a D symbol. The final approach or inbound course is shown. In this case, the course also includes a minimum altitude and distance to the nav aid. The reciprocal course is shown as a radial from the VORTAC. A dashed line represents the missed approach track. It shows the initial up and out maneuver, which coincides with the textual description of the missed approach. If a holding pattern is required for the missed approach, it is also shown with a dashed line. You can find additional information on the plan view symbols in the legend at the front of the chart booklet. Look for the page titled Plan View Symbols. Now let's turn our attention to the profile view. This portion of the chart illustrates the approach from the side and depicts the vertical flight path, facilities, and minimum altitudes in feet MSL. Minimum altitudes are shown with a line below the number, while a line above and below the number indicates a mandatory altitude. If the number does not have a line above or below, it is a recommended altitude. Finally, a line above the number indicates a maximum altitude. The profile view depicts the glide slope intercept altitude along with the non-precision final approach fix. Also shown is the altitude of the glide slope at the final approach fix. The glide slope angle or descent angle may be shown with the threshold crossing height or TCH. When there are mileage limitations on procedure turns, they are shown here. Along the bottom of the profile view, distances between fixes may be shown. These distances are given in nautical miles. On some charts, there may be a bold V depicted on the profile view. This identifies the visual descent point, or VDP. This is a point where a normal descent from the MDA to the runway can be made provided the required visual references are met. Also included in the profile view is a quick reference of the missed approach procedure. Boxed icons provide a graphic summary of the missed approach that coincides with the textual description. In this case, the missed approach calls for a climb straight ahead to 2,000 feet, then a left turn to follow the 082-degree radial of IAH to Cosby intersection, which is 21.8 DME miles from IAH. The next section of the approach chart is the landing minimums. It provides information regarding the lowest altitude you can descend to in instrument conditions, as well as the minimum visibility required for a specific approach. The landing minimums depend on the type of aircraft you're flying. Therefore, the FAA has established 5 approach categories based on approach speed. A letter designates each, with A being for the slowest approach speeds and E for the fastest. For most airports, Category E is not shown since it applies primarily to fast military aircraft. The airspeeds that define each approach category are listed in the front of the approach chart booklet. The approach speed is computed as 1.3 times the stalling speed of an aircraft in the landing configuration at maximum landing weight. Most single-engine general aviation aircraft fall into Category A. The minimums also vary with the type of nav aid being used to make the approach. The lowest minimums are for precision approaches. They are listed first, followed by progressively higher minimums for non-precision approaches. For example, the lowest MSL altitude for the straight-in ILS to runway 15 left for all approach categories is 298 feet. This is known as the decision altitude or decision height. The minimum altitude for the straight-in localizer runway 15 left approach is 560 feet for all categories. Since this is a non-precision approach, the minimum altitude is expressed as a minimum descent altitude, or MDA. For a circling approach, you may not descend below 740 feet unless you have the runway environment in sight and you're in a position to make a normal descent to the runway. The last listing on this chart is the minimums for a sidestep to runway 15 right. For all categories except E, you can descend to 560 feet on the approach to runway 15 left and then sidestep to runway 15 right for a landing, assuming the sidestep runway environment is visible and you have a clearance to land on runway 15 right. A sidestep is not authorized for Category E aircraft. Next to the minimum altitude, the visibility is expressed in either statute miles or as a runway visual range, RVR. If the visibility on the runway is determined by electronic runway visual range equipment, the minimums are expressed in RVR values. An RVR is usually a 1- or 2-digit number. To convert it to feet, add 2 zeros. For example, 24 is 2,400 feet. The figure next to the MSL altitude and visibility is the height above a certain airport reference. For a straight-in landing, it is the height above touchdown, or HAT. For sidestep approaches, the HAT is based on the sidestep runway, which in this case is runway 15 right. In contrast, the height for a circling approach is measured above the airport elevation and is called the height above the airport, or HAA. The ceiling and visibility figures shown in parentheses are used only for military planning purposes and do not apply to civilian pilots. The landing minimums usually assume that all of the necessary equipment is operational. If a component is inoperative, you must refer to the inoperative components or visual aids table at the front of the booklet to see what adjustments, if any, must be made. Now let's look at RNAV minimums. On certain RNAV charts, you may see some major differences in the descent minimum format, along with new terminology. The new RNAV chart format may include minimums for GLS, LNAV VNAV, LNAV, and circling approaches. GLS minimums identify precision approaches that require the use of the Wide Area Augmentation System to fly precision GPS approaches. They are currently not in use. LNAV, VNAV minimums are flown using a descent path generated by onboard navigation equipment. Since vertical guidance is provided, the minimums are published as a decision altitude. Use of the VNAV DA is subject to appropriate flight crew training, proper equipment, and operator approval. LNAV minimums are designed for non-precision approaches that only provide lateral navigation. Because vertical guidance is not provided, the minimums are published as an MDA. The next section of the approach chart we will look at is the airport sketch, which is located next to the profile view. The dominant feature of this sketch is the runway layout. It also depicts the airport elevation, the landing runway final approach course and distance from the final approach fix, and obstructions and reference features near the airport. Dimensions and gradients, as well as touchdown zone elevations, are shown for each runway. Approach lighting aids are shown in graphical form, as well as textual descriptions. Lighting symbols are also provided that are defined in the legend pages at the front of the approach chart booklet. Some airports, such as George Bush Intercontinental Airport, have such complex runway and taxiway configurations that a separate airport diagram is published to assist in the movement of ground traffic. Since this diagram is designed to assist pilots operating on the airport surface, it depicts ramp areas and taxiways in great detail. Taxiways and ramp areas are shaded to distinguish them from runways. The diagram also depicts latitude and longitude tick marks to help pilots update computer-based navigation systems such as INS. It also graphically shows the magnetic variation as well as the annual rate of change. Other features include the weight limits for runways and, where a displaced threshold exists, the usable landing distance. The airport diagram also lists the appropriate frequencies for ground operations. For a further explanation of the symbols used on the chart, see the legend pages in the front of the chart booklet. Below the airport sketch is the time and speed table, which provides elapsed times from the final approach fix to the missed approach point based on the aircraft's ground speed. If timing information is missing, it means the missed approach point cannot be determined by timing. In a separate descent table contained in the back of each Terminal Procedures publication, NACO provides various descent angles, ground speeds, and the corresponding rate of descent. This chart is a useful tool for planning and executing precision descents. Now that we have covered the NACO pilot information chart format, it is important to note that not all charts have been converted to this type of format. You will occasionally see the traditional NACO chart format until the entire NACO chart library has been converted. While the information presented on both charts is essentially the same, the chart layout is different. For example, on the traditional chart, the approach type and runway number are shown on the top left, while the city, airport name, and state location are on the right. All radio frequencies are listed in the upper portion of the plan view. The missed approach instructions are listed in the profile view, and any procedure notes and limitations are shown below the minimum section. The airport sketch is located on the lower right-hand side of the chart. The legend pages in the front of the U.S. Terminal Procedures booklet provide additional information about both types of charts and should be periodically reviewed for the latest changes. Every day, thousands of pilots fly instrument approaches. Safe and proper execution of instrument approaches depends on your understanding of the procedure you intend to use, as well as your ability to extract information quickly and accurately from approach charts. The specifics of an instrument approach, such as altitudes, headings, descent angles, and missed approach procedures, may vary widely from one airport to another. Understanding the fundamental elements of an approach allows you to effectively plan and execute individual charted procedures. Your planning should begin with the pre-flight review of the approach procedures for your destination, and, if applicable, the alternate airport. This will ease some of your workload later when flying the approach. Your in-flight review typically begins as you near your destination. The type of approach to expect is provided by a controller or is broadcast on ATIS.
Warrior 147, turn right heading 160, maintain 3,500, expect ILS runway 19er left.
Roger, Warrior 147, turning right to 160, maintaining 3,500. We'll expect ILS runway 19er left.
Now that you know which approach to expect, you can concentrate your in-flight review on the specific chart. Briefing strip charts provide an easy way to quickly identify the primary items during this chart review. Make sure you have the correct chart by verifying that the heading matches the procedure you're about to fly. Use the communications row to review and set the necessary frequencies you'll use throughout the approach. Use the information in the next set of rows to tune and identify the primary navigation aid, and to review the final approach course, the appropriate altitudes, and the missed approach procedure. Also check the procedural and equipment notes, and the MSA information. Next, you'll want to review the plan view to familiarize yourself with the procedural tracks, nav aids, and headings. The profile view shows the appropriate altitudes for the approach, as well as the headings and fixes along the approach course. Check the conversion table to determine descent rate information. Also, note the appropriate time to the missed approach point in case you must fly a localizer approach due to an equipment malfunction. In this section, review the approach lighting so you know what to expect when you see the runway environment. Should a missed approach become necessary, this portion of the chart provides a quick reference to the initial up and out maneuver. Finally, review the minimum section to determine the minimum altitude and visibility for the approach. The pre-flight and in-flight review of the approach helps to reduce your workload during the actual approach. It also reinforces where to find the information quickly if needed. Now let's take a look at some of the common procedures used to fly an approach. One of these is the use of radar vectors to align your aircraft with the final approach course.
Phoenix approach, Cessna 241, leaving 12,000 for 10,000.
Cessna 241, report Arlen.
Phoenix approach, Cessna 241 at Arlen.
Cessna 241, turn left heading 055, maintain 5,000 until established on the localizer. Cleared for the ILS runway 7 left approach. Contact Phoenix Tower at Reno on 120.9er.
This clearance includes 4 key elements. They are the assigned heading, the assigned altitude, a clearance for the approach, and the instructions for when to change frequencies. Normally, the final heading assignment allows you to intercept the final approach course in sufficient time to establish yourself on the course prior to the final approach fix. Maintaining the altitude assigned by the controller is very important. Controllers assign altitudes that are at or above the minimum vectoring altitude, which provides both obstacle and terrain clearance. Do not descend from this altitude until you are established on the final approach course. Your clearance for the approach means you are expected to intercept the final approach course and fly the approach as charted without a further clearance. However, at a tower-controlled airport, this is not a clearance to land from the approach. Now let's turn our attention to some of the unique aspects of non-radar approach procedures. Without radar assistance, you must follow the charted procedure to align the aircraft with the final approach course. In some cases, your direction of arrival allows you to intercept the final approach course and proceed with a straight-in approach. When this occurs, the chart indicates no PT along the route. At other times, you must execute a procedure turn or course reversal to align your aircraft with the final approach course. The most common procedure turn depicted on approach charts is the one shown here. When this symbol is shown, the method you choose for the course reversal is optional. However, no matter what procedure you use, you must remain within the protected airspace allotted for the procedure and fly the reversal on the same side of the course as it is charted. The method of course reversal for some procedure turns is not optional. When a procedural track is charted, such as this teardrop or this holding pattern, you must fly the procedure exactly as shown. Another important aspect of an instrument approach procedure is whether you can make a straight-in landing or whether you must circle to land. If a circling maneuver is required to align the aircraft with the active runway, there are several issues you must keep in mind. First, you need to know which category you will use for the approach. Remember, if you use a higher than normal approach speed, you must use the minimums for the higher category. Using the appropriate category will ensure you remain within the protected obstacle clearance area defined by the FAA. For example, the protected area for a Category A aircraft is a 1.3 nautical mile arc measured from the end of each usable runway. It also includes the tangent areas. The area for Category B aircraft extends out to 1.5 nautical miles. The obstacle clearance area for Category C aircraft extends out to 1.7 nautical miles. And Category D arcs extend to 2.3 nautical miles from the end of each usable runway. The base of each area is the circling minimum descent altitude specified on the approach chart. So you can see that it's very important not only to maintain the minimum altitude while circling, but also to stay within the protected area for your category of aircraft. Do not descend from the MDA until you have the runway environment in sight and your airplane is properly positioned to make a normal descent to the landing runway. Another unique feature of every instrument approach is the missed approach procedure. It is carefully designed to provide adequate obstacle clearance throughout the segment. Although limited visibility is the primary cause of most missed approaches, you can initiate the procedure for a number of reasons. such as not being properly aligned with the approach course, or receiving specific instructions from ATC.
Cessna 241, execute missed approach. We have a disabled aircraft on the runway.
Beginning a missed approach before you have arrived at the MAP requires special consideration. For example, let's assume you decide to execute the missed approach between the VOR and the 2.8 DME fix. The charted missed approach procedure calls for a straight-ahead climb to 2,100 feet, then a left turn direct to the Mount Vernon VOR, followed by a hold. However, the missed approach segment does not begin until the missed approach point. Therefore, you must delay the turn until you reach the MAP. There is no restriction on climbing early, but an early turn may not provide the necessary obstacle clearance. Another situation that requires special attention is a missed approach during a circle-to-land maneuver. If you lose sight of the runway during a circling maneuver, the AIM recommends that you make an initial climbing turn toward the landing runway. Once you've landed, you must make sure your IFR flight plan is closed. At an airport with an operating control tower, your flight plan is automatically closed for you. At airports without an operating control tower, you must close your flight plan either by radio contact or through a phone call to the nearest flight service station or ATC facility. The foundation for instrument approach procedures comes from the Federal Aviation Regulations and other official FAA documents, such as the Aeronautical Information Manual. It's important to study these sources frequently to keep the procedural side of your IFR skills in top shape.
Many instrument approaches are based on nav aids that do not provide glide slope information. They are classified as non-precision approaches. There are two general types of VOR approaches. Some have the nav aid located at the airport so that your final approach segment ends at the VOR. Others have the VOR located away from the airport. Your final approach segment is either to or from the station and ends at the runway. Another consideration with non-precision approaches is whether you can land straight in from the approach or if you need to circle to land. Some approaches have the final segment closely aligned with the runway. In most cases, you can make a straight-in landing from these approaches. When the final segment does not meet the criteria for a straight-in landing, a procedure called a circle-to-land maneuver is usually required to align your aircraft with the runway. Another concern is whether or not DME is available or required for the approach. Since there is no such thing as a typical VOR approach, you must study each chart before using it. With that in mind, let's look at the VOR runway 31 approach into St. Cloud, Minnesota. Your present position is on the feeder route from Daly intersection. Minneapolis Center has cleared you for the approach, and you have received the current altimeter setting from St. Cloud Unicom. The minimum altitude for this feeder route is 3,000 feet. Your inbound course to St. Cloud is 222 degrees. Once you're established on the course inbound to St. Cloud, and if your aircraft is equipped with dual VOR receivers, set both to the St. Cloud VOR and identify the station. In this example, the number 1 nav is being used to fly to the VOR, and the number 2 receiver is set to the outbound course from the initial approach fix. As you pass over the station, make a left turn to intercept the radial. The profile view shows that once you're established on the outbound course, you can descend to 2,700 feet and complete your procedure turn at that altitude. The procedure turn must be completed no further than 10 nautical miles from the VOR. With DME equipment, you can easily keep track of your distance from the station. Without DME equipment, a 2-minute outbound leg is recommended for most light single-engine airplanes. Of course, you may need to adjust this time based on your ground speed. The procedure turn is completed by flying 073 degrees for 1 minute, then making a 180-degree right turn to a heading of 253 degrees. During this procedure, set the VOR indicator to the inbound course of 298 degrees. When the CDI begins to center, turn right to intercept the final approach course and adjust your heading to keep the needle centered. You may now begin your descent to 1,480 feet. Note that if you are unable to obtain a local altimeter setting and must rely on the one provided by the Princeton Flight Service Station, you cannot descend below 1,560 feet. Also, notice that this approach does not have timing information. Since the nav aid is located on the field, it is the missed approach point. Now let's look at another chart that has timing information. Many VOR approaches require you to determine the missed approach point through timing. In this example, if DME is unavailable, you should begin timing once you reach the final approach fix at Maddie intersection. At a ground speed of 90 knots, you'll reach the missed approach point in 3 minutes and 24 seconds. Now let's go back to your position on final approach into St. Cloud. Although DME is not required for this approach, you'll be able to descend to a lower MDA if you have the equipment. If you can identify the 1.8-mile DME fix, you're authorized to use a minimum descent altitude of 1,420 feet. Without the 1.8-mile DME fix, the MDA is 1,480 feet. Once you reach the MDA, you may not continue the descent unless you have the prescribed flight visibility and required visual references in sight. Furthermore, you must be in a position that allows you to descend to landing at a normal rate. If you're unable to identify the runway environment upon reaching the missed approach point, you must immediately execute a missed approach. The missed approach procedure calls for a climb to 2,700 feet, then a right turn direct to the St. Cloud VOR DME. If you reach the VOR prior to receiving an additional clearance, you must enter the depicted holding pattern. Although DME was not mandatory for the flight into St. Cloud, many VOR approaches require DME, such as the VOR DME runway 28 right approach at Billings, Montana. When DME is required, it is indicated in the chart heading. The plan view shows that in addition to the procedure turn, either of the two 16-mile DME arcs can be used as the initial approach segment. For this approach, DME is required to identify the initial approach fix, final approach fix, and the missed approach point. Likewise, timing information is not given since the missed approach point is identified by DME.
The next type of instrument approach we'll consider uses navigation signals transmitted from a non-directional radio beacon. These signals are displayed on your ADF indicator and are used to fly NDB approaches. An NDB approach is classified as non-precision since it does not provide glide slope information. Your ability to fly this type of procedure gives you access to hundreds of airports not served by VHF equipment. You'll also find that NDB approaches are frequently available at airports that already have ILS and VOR approaches. For that reason, they are often considered backup procedures, since they provide an alternate means of descending to the airport in case of VHF navigation failure. An ILS approach procedure may incorporate a compass locator at the outer marker. At many airports, this same nav aid is used for the NDB approach. In this case, the station is located away from the airport, which requires a timed approach. At other locations, the NDB is positioned at the airport, where it normally becomes the missed approach point. Now let's use your knowledge of ADF to fly the NDB runway 27 approach into Henry County Municipal Airport at Newcastle, Indiana. By carefully studying the chart, you'll notice that this procedure is not authorized at night. You'll also see that this particular approach does not provide timing information for determining the missed approach point. Since the NDB is located at the airport, the missed approach point is at the station. Let's pick up the flight as you near Nudo intersection with a clearance from Indianapolis Center to fly the NDB runway 27 approach. Henry County Unicom has given you the current weather and altimeter setting. With a movable card ADF, set your current heading on the azimuth index. You'll know you're at Nudo when the needle points to the 107-degree magnetic bearing shown on the approach chart. If you have a fixed card ADF indicator, you must add your magnetic heading to the relative bearing to find the magnetic bearing to the station. If your magnetic heading is 081 degrees and the magnetic bearing to the station at the intersection is 107 degrees, your indicator should read 026 degrees when you reach Nudo. Notice how this is the same 26-degree relative bearing that you get with a movable card indicator. Once you're established on the feeder route and are cleared for the approach, you can descend to 2,700 feet. During this segment, you should find the combination of magnetic heading and relative bearing needed to maintain the 107-degree magnetic bearing to the station. After reaching the NDB, you need to turn right slightly and track outbound on the 112-degree magnetic bearing from the station. Fly the outbound leg for approximately 2 minutes before beginning the procedure turn. Adjust this time as necessary to remain within 10 nautical miles of the nav aid. The minimum altitude for the procedure turn is 2,700 feet, which is the same altitude you were at for the feeder route. To perform the procedure turn, turn left to 067 degrees for 1 minute. Then make a 180-degree standard rate turn to a heading of 247 degrees. If you fly the procedure as charted, you will intercept the inbound course at a 45-degree angle. If you're using a fixed card ADF, course interception is shown when the needle points to a 45-degree relative bearing. On the other hand, with a movable card ADF, you set the heading for the second half of the procedure turn under the top index. When you reach the 45-degree intercept angle, the needle points to the 292-degree magnetic bearing to the station. In actual practice, you'll lead the course interception to roll out on the inbound bearing. You can initiate a descent to the minimum descent altitude once you're established on the inbound course. Determining the MDA involves a couple of steps. Since the approach is for a straight-in landing to runway 27, these minimums apply. Because you were provided a local altimeter setting, you can use the lower MDA. As you near the missed approach point, there are many things to consider. For this particular approach, you know that the runway is left of the NDB. So, as you scan for the runway, you must consider your heading as well as the actual location of the airport in relation to the final approach course. If you enter VFR conditions, maintain a normal scan for other traffic. This is particularly important at an uncontrolled airport. In any case, don't descend below the MDA until you're in a position to make a normal approach and landing. If you reach the NDB without positively identifying the runway environment, or if you are not in a position to make a normal approach and landing, you must execute the published missed approach procedure. The missed approach calls for a climb to 2,700 feet. Then a left turn direct to Newcastle NDB. And hold. Another type of instrument approach we'll look at uses navigation signals transmitted from a series of satellites. A GPS receiver determines its position in terms of latitude and longitude by knowing the precise location of each satellite and accurately measuring the time a signal takes to travel to the receiver. A minimum of 3 satellites is required for lateral guidance, while 4 are needed for both lateral and vertical guidance. The signals are displayed on a conventional VOR indicator or a digital indicator and are used to fly non-precision, non-localizer instrument approach procedures. With this in mind, let's take a look at how GPS is used to fly a non-precision instrument approach. Because there are a large number of GPS receivers available and each displays position and navigation information differently, you must be thoroughly familiar with the specific equipment installed in your aircraft, as well as its limitations. To fly a GPS approach, there must be a published procedure, and the approach must be retrievable from your GPS database. The database contains waypoints representing all fixes on the approach and displays these points in the same sequence as they are presented on the chart. If a final approach fix or step-down fix is not named in the approach procedure, a sensor final approach fix is established at least 4 nautical miles from the missed approach point. These sensor fixes are identified in the database and appear on Jeppesen charts, but do not appear on NOS approach charts. Flying a GPS procedure is identical to flying a traditional approach. The same approach track is flown and the same minimums apply. The benefit of GPS is that approaches can be developed at airports that do not have the ground-based equipment necessary for a conventional approach. For example, this approach at Frederick, Maryland is based entirely on GPS. In this situation, the approach procedure is comprised of several fixes that are contained in a GPS database. As you practice, you'll find that using GPS equipment to fly instrument approach procedures is as simple as navigating with traditional equipment. Although VOR and NDB approaches do not have the precision and lower minimums provided by an ILS, they are still an excellent way to descend to an airport in IFR conditions. The Instrument Landing System, or ILS, is called a precision approach, since it provides both course and vertical guidance information. Because it's so accurate, you can usually descend to a lower minimum altitude than with other approach procedures. Lateral guidance is provided by the localizer, which radiates a navigational signal along the runway centerline. When the signal is projected in this manner, it is called a front course localizer. Just like a VOR, you should identify the localizer by listening to its Morse code identification, which consists of 3 letters preceded by an I. This is especially important when 2 or more localizers are operating in close proximity to each other. For example, the localizer for the ILS runway 27 left approach at Miami International can be identified by IMIA. While the identification of the localizer for the ILS runway 27 right approach is IVIN. Inside the cabin, course guidance is provided by the course deviation indicator on your VOR equipment. When you are flying inbound along the front course, the CDI tells you if you're drifting left or right of the runway center line in much the same way as when flying along an airway. However, with an ILS, the instrument is much more sensitive. On a typical ILS, full-scale deflection occurs at 2.5 degrees rather than the normal 10 degrees with VOR. Theoretically, then, you should be able to track the localizer course 4 times more accurately than a VOR radial. With increased sensitivity, the CDI reacts more rapidly. Therefore, you will need to make smaller course corrections and make them more promptly. A unique characteristic of the localizer signal is that it provides only one magnetic course to the runway. This means that no matter where you set the OBS, the needle senses your position only in reference to the specific localizer course. In actual practice, it's a good idea to set the published ILS course on the azimuth ring as a reminder of the proper course and to help with heading corrections. The localizer also transmits a signal in the opposite direction, which is called the back course. Navigating on this segment requires special considerations. The only time you are authorized to navigate along a back course is when an approved instrument approach procedure exists and you have a clearance to fly the procedure. When you fly inbound on the back course, you experience reverse needle sensing on the indicator. This means you have to fly away from the needle to return to the localizer. Reverse sensing also occurs when you fly outbound on the front course. A simple rule to remember is that whenever you're flying on the same heading as the front course, normal sensing occurs. This means that when you are inbound on the front course or outbound on the back course, you correct toward the needle. When you fly a heading opposite to the front course, you must correct away from the needle. This occurs when you are inbound on the back course or outbound on the front course. Some localizer indicators are able to compensate and give you normal sensing during back course approaches. During an ILS approach, vertical guidance is provided by the glide slope. This signal allows you to navigate along a glide path to the runway. The glide slope transmitter and antenna are usually located to the side of the instrument runway center line and 750 to 1,250 feet down the runway from the approach threshold. Normally, this signal is only directed to the front course, and since it is offset from the runway, it may not provide guidance all the way to touchdown. The transmitter operates on a UHF frequency, which is paired to the associated VHF frequency. When you select the localizer, you automatically select the associated glide slope. The center line of the glide slope is usually adjusted to an angle of 3 degrees above horizontal. However, this angle may vary slightly due to local conditions. False signals can also be generated at high angles. This usually isn't a problem if you intercept the glide slope at or near the altitude and position prescribed on the approach chart. On the ILS indicator, the glide slope is displayed by a horizontal needle. It operates similar to the CDI in that it shows your position with respect to the correct glide path. If the needle moves up, you are below the proper glide slope. If it moves down, you are above the glide slope. Fly toward the needle to return to the proper glide slope. The combination of the localizer and glide slope allows you to visualize your position along the final approach path. For example, this is the indication when you drift left and above course. To return to the proper approach path, you need to turn right and descend. An ILS also includes 2 or more marker beacons to provide you with range information along the final approach segment. The outer marker is placed between 4 and 7 nautical miles from the runway. Generally, the outer marker is placed at or near the point where you intercept the glide slope. The exact location is identified on the specific approach chart. A receiver in the airplane provides both an audible and visual cue when you pass over a beacon. The outer marker is identified by a flashing blue light and a continuous series of dashes. The middle marker is usually placed 3,500 feet from the landing threshold and intersects the glide slope at approximately 200 feet above the touchdown zone elevation. The middle marker is identified by a flashing amber light and alternating dots and dashes. Some approaches incorporate an inner marker that is identified by a white light and a series of dots. It allows certain qualified operators to fly an ILS approach to lower than normal minimums. Many ILS systems incorporate a compass locator that functions like an NDB to provide additional navigational information. Normally, it is co-located with the outer marker, although it might be placed at the middle marker as well. The compass locator may be used as a nav aid for the transition to the terminal environment or as an additional means of orientation during final approach. Some ILS approaches use DME to help you monitor your distance to the runway, as well as to provide a substitute for some of the ILS components. Where DME is required for the approach, it is indicated in the procedure name. The basic ILS is called Category 1. This type of approach is available for use by all current instrument-rated pilots. Normally, the minimum visibility is 1/2 statute mile, or an RVR of 2,400 feet. When centerline lights and touchdown zone lights are provided, the minimum visibility can be reduced to 1,800 feet. The decision height is usually 200 feet above the touchdown zone elevation. A Category 2 or 3 ILS requires special certification of pilots, operators, aircraft, and air and ground equipment. Category 2 approaches normally provide for a descent down to 100 feet above the touchdown zone elevation and an RVR of 1,200 feet. Category 3 approaches allow descents down to the runway. They are further divided into RVR categories, with the lowest requiring no RVR minimums. Because of the complexity and high cost of Category 3 equipment, this type of approach is used mainly by air carriers and the military. Now let's use your understanding of the ILS components to fly an actual approach. We'll use the ILS Runway 4 approach at Amarillo, Texas. Assume you are on the feeder route from Cider intersection and have been cleared for the approach. The procedure will be shown as if it were in a non-radar environment. The feeder route requires you to track the 093-degree bearing to the Pandy LOM. Since you've been cleared for the approach, you may begin the descent to 5,300 feet. During this segment, you tune and identify the ILS approach facility, set the final approach course, and test the marker beacons in the airplane. As you near Pandy, you have a number of ways to identify the LOM. For instance, the localizer needle begins to center, and the ADF bearing indicator starts to move away from the nose. As you pass over the station, the marker beacon light flashes, and you hear the identifier. Instead of intercepting the localizer inbound, you must turn right, track outbound on a course of 217 degrees, and fly the procedure turn. Since you must remain within 10 nautical miles of Pandy, you should begin the procedure turn as soon as practical. A 2-minute outbound leg is usually sufficient to establish the course before you start the turn. The minimum altitude for this segment is 5,300 feet MSL.
Amarillo approach, Warrior 312 is Pandy outbound.
Roger 312. Report Pandy inbound to the tower on 118.3.
Warrior 312, report Pandy inbound on 118.3.
As you fly outbound, remember that you'll have reverse sensing on the CDI. If you drift from course, you'll have to fly away from the needle to return to the localizer. The approach chart shows the side of the localizer and the recommended headings to fly during the procedure turn. You can make the course reversal by flying to 172, then 352 degrees. As you complete the turn to a heading of 172 degrees, you should note the time, since the recommended length for this leg is 1 minute. When you have completed the initial part of the procedure turn, make a 180-degree right turn to 352 degrees. You can verify that you are approaching the inbound course when the CDI begins to center, and the ADF nears a relative bearing of 45 degrees to the Pandy LOM. Your minimum altitude from the procedure turn inbound is still 5,300 feet until you intercept the glide slope just before you reach Pandy. Your primary concern at this time is to stabilize your airspeed and altitude, and find the heading that maintains the localizer centerline. Intercepting the glide slope at the proper speed makes the descent more stable. This is also a good time to verify the decision altitude and height for the approach and the missed approach procedure. As you near the glide slope intercept point, the horizontal needle begins to move down towards center. As the needle centers, you must make a small pitch, power, and trim adjustment to establish the proper descent rate and maintain the airspeed. It's a good practice to note the time as you pass the outer marker. If the glide slope stops working, you can still continue with a non-precision localizer approach, since you'll have the timing needed to identify the missed approach point. This table provides timing information to the missed approach point, as well as the rate of descent for the approach. If you are stabilized on the glide slope, you can verify your ground speed by comparing your actual rate of descent with the table. For example, when established on the glide slope, you note that your VSI is indicating a 510 foot per minute descent rate. Since this indication is about halfway between the corresponding rates for 90 and 100 knots, you can estimate that your ground speed is approximately 95 knots.
Amarillo Tower, Warrior 81312 is Pandy inbound.
Warrior 312, cleared to land, runway 4.
As you continue down the glide slope, you should monitor your progress toward the decision altitude and height. As you approach the decision altitude, begin to look for the approach lights and other indications of the runway environment. The missed approach point on this ILS is located where the glide slope intersects the decision altitude of 3,805 feet. If you have the required visual references clearly in sight and can make a normal landing at this point, you can continue the approach. If not, you must immediately execute a missed approach. Even with the runway in view, don't completely disregard your instrument scan as you descend to land, since it's possible to enter low-level clouds or fog. When compared to other types of instrument approaches, the ILS offers a better opportunity to complete your approach and landing in poor weather conditions. When you combine the precision provided by the ILS with careful pre-flight and in-flight planning, you will find that flying the approach is both simple and easy.